Hey, welcome to Calculus, AP Calculus, Chapter 5, Section 1. This is Day 2. On Day 1, we talked about how we find extreme values. And finding extreme values, that includes our absolute maximums and minimums, includes our local maximums and minimums, which I sometimes refer to as relative maximums and minimums. And we found to find those, we have to consider any endpoints, which we're going to talk about in just a moment. And we have to consider critical points, which includes where the slope is 0 or points of non-differentiability. Endpoints, real quickly. Sometimes endpoints are just given. Like we could have this function and it could just say, hey, by the way, x is greater than or equal to 0 and x is less than 7. So we put 0 in, we put 7 in, because there's very likely, great likelihood that endpoints contain maximums and minimums of a function. Most functions, I shouldn't say most, but many functions, if there are endpoints to them, or if we create endpoints, state endpoints, endpoints will be maxes, mins. If you look at B, sometimes they aren't stated, but they are implied. On quick inspection, and we may have to do some more algebra than this at times, but on quick inspection I realized 2 is an endpoint, because if x gets bigger than 2, I'm taking 4 minus a value bigger than 4, trying to take the square root of that. So x has to be less than or equal to 2. 2 is okay. And if I put negative 2 in here, I have the same issue. X has to be at least negative 2. 0 is okay, 1 is okay, negative 1 is okay, 1.99999 is okay, but 2.0001 is not okay. So sometimes we have to do that. So for example B, the points I'm going to test, I'm definitely going to find f of 2 here, and I'm definitely going to find f of negative 2 here to see if those are possible maximums or minimums. And we're going to be graphing along with this. We'll check some of these in our graphing calculator. Okay, so first let's consider endpoints. To do that, we might want to be talking about, are there any implied endpoints here? Well, I can add 2 to any number I want. I can square any number I want, and I can take the third root of any number I want. I can multiply any two numbers I want. All values of x are fine for here, and therefore there are no endpoints. I'm going to distribute this through, and I get x to the 5/3 plus 2x to the 2/3, and there's some interesting future conversations that are going to occur with this curve. But here's what I know about it. This x to the 5/3 is almost x to the second. This wants to be nearly curve-wise, nearly like a parabola, positive parabola, at least to the right. As I go to the left, I get negative values. But it definitely wants to be curving in an upward fashion, and this one is less than to the first, so it wants to be more like a square root. But as x gets bigger and bigger, this is going to take precedence over that. So what I'm trying to state here is our limit of y as x approaches infinity. This thing is the more powerful, the more dominant player here. As x approaches infinity, the limit is going to approach infinity. So I know we're going to go off the chart here. Therefore, we have no absolute maximum. And how about the limit? So that guy approaches infinity. How about the limit as x approaches negative infinity of y? So as we move to the left, I get big negative, and this keeps it as big negative over smaller positive. So I get bigger negative versus smaller, relatively smaller positive. It's going to go negative. It's going down forever as well. All right, so we'll come back to that. We have to consider that, because what that's telling me is we have no absolute maximum, no absolute minimum. So next, critical points occur when slope is 0 or points of non-differentiability. So guess what we're going to do for both cases? This is good news. 3 types of points to consider, but 2 of them come from the same test. We're going to find our derivative. So y prime is, I could product rule this, or I could find the derivative of this with power rule. I'm going to power rule. And I get 5/3 x to the 2/3 power plus 2/3 times 2, 4/3 x to the negative 1/3 power, or y prime equals, I'm going to write these as fractions, 5x to the 2/3 on 3 plus 4 in the numerator. Because x to the negative 1/3 is a factor of this, I can put it in the denominator on 3x to the positive 1/3. For common denominators, I need a factor of 3. I need a factor of 3. I've got it. I need a factor of x to the 1/3. I don't have it. So this 5x to the 2/3 needs to be multiplied by x to the 1/3 on x to the 1/3, and then that's kind of convenient. I get 5x plus 4 didn't have to be multiplied by anything. It was already over our denominator. So here's what I'm looking for. I'm looking for points of where the slope is 0. Slope equals 0 when 5x plus 4 equals 0, or when x equals negative 4/5. So my critical points include x equals negative 4/5. That is a slope is 0. That's a leveling off point. It might be a maximum or minimum. And non-differentiability. Well, non-differentiability is based on my domain of the derivative. In my domain, x cannot equal 0, and because x can equal 0 up here, put in 0, get out 0, it's a critical point. Now, let's study and think about that one for a minute. In fact, before we do that, let's go over to our graph and let's take care of what we could hire out an Algebra 1, second semester Algebra 1 student and do this and say, what are the zeros? Well, when x is negative 2, we got a 0. When x is 2 with 0, 0 to the 2/3 is 0. So points I'm going to consider for maximums and minimums now would be f of, I'm going to start with 0 just because it's an easy one. F of 0 gives me 0. So this could be a max or min. Now let's come back and let's take a look. Let's dissect this a little bit. If I put a number just a little bit bigger than 0 in here, I get basically 0 plus 4. I get a little bit more than 4 over a tiny, tiny positive number, which means my slope wants to be 4 over 0-ish or positive infinity. It wants to come out of here with slope positive infinity for an instant. Don't know if you can see that over here, but we're coming out of there really steep. And I'm not trying to get my y-axis to any particular scale. So we're coming out of here really steep. Okay. Now, my sprinter in this wants to look like a root function. So it's going to level off, but eventually my sprinter is going to give way. And I don't know what the graph of this necessarily exactly looks like, but eventually it wants to head up. And again, I don't have a y scale. I'm not saying that the 0.48 is on the graph. Not saying that at all. But we're going to look something like that. Okay, let's find f of negative 4/5 between here and here. Or let's even go back before we do that. Let's go back to our derivative. What happens when I put a tiny, just barely to the left of 0 negative number, negative 0.00001? I get a negative in the denominator, but I still get a value close to 4 in the numerator. I get close to 0 but negative, and I get close to 4. 4 divided by close to 0 wants to be infinity, but negative because the value down here would be negative. Oh, so slope coming in here is negative infinity. Wants to be like negative. It can't really say it is negative infinity because infinity is a concept, not a number. Okay, so it's going to go up. It's going to level off. Where is it going to level off? I guess at negative 4/5 because it has to come back down to 0. Let's see what f of negative 4/5 is. I get negative 4/5 to the 2/3 times 4/5, negative 4/5 plus 2, or I get, that would be 16/25 when I square them, but third root of those. And this would be negative 4/5 plus 10/5, 6/5. And here's what I know about this. I know 16/25, the third root of that, it's close to 1. And 6/5 is close to 1. I get close to 1. I'm going to jump to calculator here and just grab this value. Let's take a look here. I think you can see that. When I put in 16/5 to the 1/3 times 6 divided by 5, I get 1.0341. So right here at negative 4/5 I come up just a little bit bigger than 0. I got a leveling off point. Where do I go from there? Well, I'm claiming the graph is continuous. Might it go up, level off, and come back down? That's what's overlooked by people too many times. There are only two zeros, 0 and negative 2, so I can only pass through the x-axis at these points. And there's only one leveling off point, so there's no way I can go up, level off, and come back down. And I don't hit a corner point and come back down, because the only place I have leveling off points or corner points are right here. So this thing has to look like this, come back down here, and this is going to take over eventually, and it's going to look steeper than a first degree. It's going to get steeper than a first degree. The graph of this looks something like this. Okay, so here's what we've learned. We have a relative minimum at 0 of 0, or the point 0, 0. We have a relative or local, these could be called locals, maximum at negative 4/5 of third root of 16, get it together, 25ths times 6/5, or the point negative 4/5, if you like, approximately, what do we decide, 1.0341. I probably should round that to 3 decimal places. Okay, and we have no absolute max, absolute min. Now let's go to the curve. So if I go into y equals, I've got this guy plotted already. X to the 2/3 plus 2, x to the 2/3 times, x plus 2. I'm going to zoom standard that. Let's take a look. We got it. There were some things that, ooh, that's kind of interesting. It does, take a look at this. I don't know if you saw that little swing. It does look like it comes out steeper, levels off a little bit, swings back up, and that's a discussion for another time that involves the second derivative. We'll be coming into that in chapter 5. But what I'm looking for right now is my max min. So I'm going to go zoom box, one of my favorites, build a little TV screen around my max and my min, somewhere about here, down to there. Enter. And I don't think I need to test the value at, I don't think I need to test for a minimum at 0, 0. I think that's pretty clear that that's what we have, but I'm going to find that max. Second calc maximum. Let's get left. Let's get to the right. Let's stamp enter and hope that we get, what's our target? 1.0341. And can we see it? 1.0341. And we got them. Okay, so that's what we're going to be doing there. What do we think? There's a lot going on there. It took some time. We're 12 minutes into this video. And one problem, was there a hard aspect about that? No, there's just a whole lot of easy. And that's what calculus is about to become for us. Just a whole lot of easy and some organization along the way. Okay, let's take a look at example 2. So example 2, we already talked about 2 and negative 2 being endpoints here earlier on in this video when we were discussing endpoints, critical points. So I'm going to go ahead and just find those values now and just get them on the graph. Well, when I put 2 in, I get 4 minus 2 squared, 4 minus 4, 0 squared is 0, 0 times whatever, 0. And when I put in negative 2, I get 0 as well. So I have endpoints here and there. Those are stopping points of the graph. And now I need to consider critical points, and the good news on critical points, it's both based on the derivative. So I'm just going to change this to y equals x times square root of 4 minus x squared to the 1/2. Some people mistakenly put y prime here and then say, okay, I'm going to simplify it. This is not y prime, this is still just y. Now y prime is, I'm going to product rule this. First times derivative of second times our baby function plus derivative of first, which is just 1, times our just plain second, 4 minus x squared to the positive 1/2. And now we go into algebra land. In algebra, this is a term, and within this term, everything's factored. Therefore, I can play the numerator-denominator game with this negative exponent. I've got numerators of x squared. I've got a denominator of 2, but that's divided by negative 2, just negative 1. So I get a negative x squared. This can go to the denominator. 4 minus x squared to the positive 1/2. Plus everything in the numerator. 4 minus x squared to the 1/2 on 1. Common denominators. I'm going to get a common denominator here of 4 minus x squared to the 1/2, or square root of. This was already on it. So this one I had to multiply top and bottom by 4 minus x squared to the 1/2. Good news. Something to the square root times the same thing to the square root is just the something, so I get plus 4 minus x squared. Were those parentheses necessary? No, they're superfluous, but however, had this been minus, then I'd need them. Okay, so I end up with y prime is negative x squared minus x squared, negative 2x squared. There's a plus 4, and all is over 4 minus x squared square root, or to the 1/2. So, where is the slope 0? I think I'm going to put that right here. Flowchart, not my favorite. The slope is 0 when negative 2x squared plus 4 equals 0. That is x squared equals negative 4 divided by negative 2, 2, or x is plus or minus root 2. So those are critical points. Those are other points I want to test up here. I want f of root 2 equals. All right, let's just go through with that one. I put in root 2. It's not so bad. I get root 2 times square root. I think I'll just turn this into a square root of 4 minus root 2 squared. 4 minus root 2 squared, that's 2. That's square root of 2 times square root of 2, that's 2. F negative root 2 is going to be negative 2. You can check that out. So at root 2, 1.4, I am up at 2, and it levels off there. And at negative root 2, negative 1.4-ish, I'm down, and it levels off there. Real quickly, we can see we got a 0 at 0. Could have passed that off to an Algebra 1 second semester student. We got a 0 here. Does it level off anywhere else? No, that's the only place it levels off. Now, let's go back and talk about points of non-differentiability. X cannot be 2 here. It can be 2 and live on the curve. When I put 2, let's say I put 1.999999, something really, really close to 2. When I put in something really close to 2, I get something really close to negative 4 on really close to a positive value that's close to 0. The slope is negative, wants to be negative infinity, or wants to approach negative infinity. So as I'm coming down in here, it's getting super steep, which it almost had to. How about when I get to something like negative 1.99999? When I get to negative 1.99999, I get a value just slightly less than 4, 1.99999, slightly less than 4 over my, excuse me on that one. Let me come back to that. Let me come back to that in just a moment. So we've got a curve that's coming down here, flattens off, comes up here, comes down out of there. Okay. We've got a flattening out point here, a flattening out point here. I believe those are maxes, those are mins. Still need to come back and discuss our derivative down here. So what I have is I have a absolute maximum at root 2 of 2. I have a maximum. I have an absolute minimum at negative root 2 of negative 2. And how about these guys? You say, well, those aren't maxes and minimums, and you would be right, but they are relative maxes and minimums. This relative to where we live, if this is like a house at the end of the block, relative to where we live, this is the cheapest house. So we have a relative or a local min at 2 of 0, and this one is the most expensive house on the block. Here we have a local max at negative 2 of 0. Let's take a look at that function. Let's go on. We're just confirming things here. Y equals, so let's put this one in. We've got x times square root of, let's just clear that out and start over. X square root of 4 minus x squared. I'm going to zoom standard that guy. I could just do it negative 2 to 2. Actually, I think I'll do that. Since we know the domain, I could go window like negative 2.1 to 2.1 and then zoom fit it, which is zoom 0. What we got there? Oh, pretty good representation of what we had. Notice what's happening on our curve here is it looks like it doesn't go to like all the way up to 2, but if I go second calc value and I want the value at 2, it does tell me it's 0. So it's just getting so steep there that the next step it takes steps me across 2. So got to be smarter than our calculator in that case. It actually exists. What if I go 2.00001? It's going to tell me why it stops existing there. I don't know if you can see that. Okay, so everything confirmed there. The slope thing that I was talking about, that's something that's going to be a discussion that we're definitely going to want to be involved in. But that ultimately is a discussion that we're going to look at as we move forward. Okay, let's take a look at example C. And now we have, I believe maybe we talked about piecewise functions a little bit earlier in this lesson, where we might have some corner points. So on a piecewise function, first we want to consider endpoints. Well, the end of this piece is at 1 and the beginning of this one is at 1. What I might have is a jump. Maybe I have a curve that looks like this, and then I have to jump down and proceed from down here, in which case the extreme value theorem doesn't apply. So first thing I'm going to do, I'm going to treat this top half as though it was F1 and the second one as though it was F2. I'm going to see if at 1 we're in agreement, if we're coming together or if we're jumping. So F1 of 1 is the opposite of 1 squared minus 2 times 1 plus 4. Opposite of 1 squared is not negative 1 squared. It's the opposite of 1 squared. Negative 1 minus 2, negative 3 plus 4 is 1. And the F2, if I was allowed to put 1 in there, because that's where I'm going to pick up and either have a circle after a jump or I'm going to pick up from that same value here, I get the opposite of 1 squared plus 6 times 1 minus 4. I get the opposite of 1 squared is negative 1 minus 4, negative 5 plus 6. We're at 1. So it is continuous. I don't have to pick up my pencil or pen to draw this thing. I just draw to a height of 1. We got a point at 1, 1 clearly. I draw to that point, and then I'm going to jump onto the other curve. Now, might it be going in the same slope? I could test the slope at those curves, but I know something about this. I know this is an upside down parabola. I know this is an upside down parabola. I'm not the same parabola. So when I hit at 1, 1, I can't be at the same slope because they only have the same slope for that same instant. So what we have here is a corner point, and we'll discover that as we move on. Okay, so here I'm going to deal with F1. I'm going to find F1 of X's derivative. And I'm going to remember for this part, X has to be, I can only accept values where X is less than or equal to 1. So F1's derivative is negative 2X minus 2. That is differentiable forever. So here's where I could test the slope at 1 if I wanted to. But what I want to know is when is the slope 0? The slope 0 when negative 2x minus 2 equals 0, or when x equals negative 1. So critical points to test would include 1 which is our potential corner point, would include -1, which is where the graph levels off. And let's take a look at f2 prime of x, or the derivative of the second possibility. Derivative of this, -2x plus 6. Set that equal to 0. When is the slope 0? When -2x plus 6 equals 0. When x equals -6 on -2, 3. So I want to test 3. To be honest, knowing what we know about these curves, we could have come up with these values by just doing -b on 2a. That would be 2 on -1. That would be -6 on -1. Oh, -b on 2a. Sorry. That would be -2 on... that would be 2 on -1 times 2, 1. This would be -6 on 2 times -1, -2, 3. -6 on -2, 3. We could just do, because we know they're parabolas, so we know we have a vertex. So, critical point at 1. Got it. Already found that one. So now let's find f of -1, and I get the opposite, we'll call it f, because that's f1 of -1, because it goes into here, and I get the opposite of -1 squared minus 2 times -1 plus 4. Let's see, that's -1 plus 6, 5. So at -1 I'm up 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, now it's just graphing this parabola now. Take a look. This is upside down and standard growth. The standard old parabola goes over 1 down 1, which emphasizes we have a point at 0, 4 here. It comes down to here. This is our vertex, therefore we have a mirror line. We're going to go through this point, we're going to go through this point, and forevermore we're going down. Let's take a look at f of 3. So that would be f2 of 3. I get the opposite of 3 squared plus 6 times 3 minus 4. That is -9 plus 18, 9 minus 4, 5. And I just figured out what we have here. We have the McDonald's arches. Not one of my sponsors, but if they want to sponsor me, they can. We are over 1 down 1 because it's an upside down parabola. We have this same point right here. We have a mirror line. This graph looks like this. And therefore we have, because this goes down forever, we have an absolute max of 5 at -1. We also have an absolute max of 5 at 3. And we have a relative min of 0 at, of 1. I was thinking of the last problem, of 1 at 1. So, McDonald's arch problem, good one there, a lot going on, but it's nice to be working with parabolas on that. Okay, and example 2, pretty cool problem. If you were in pre-calculus last year, good chance you worked with volume of a box problem. So what we have there is if we imagine this thing was a box, what we could do with this thing is we could cut the corners in a little bit and fold it up on each side, and then so this would just be like a piece of not a box, but a piece of cardboard, folded in on the sides, and then we'd end up with a box. And the box, so what we've got, this is probably just length times width times height, or height times width times length, something like that. So anyway, this is our volume. What we typically would want to do with a problem like that would be maximize the volume of the box. Clearly, if I don't take any cuts out of the corner, I can't fold this thing in and have it become a box and have height. We'd have volume 0. Now they tell us 0 is less than x is less than 5. Otherwise, this function exists forever. But we're only really interested in this function from 0. I'll get this down. I should get a straight edge, but from 0, definitely should get a straight edge if I'm going to draw it like that. We're only interested from there over to 5. Now let's not get so calculus heavy that we forget about the easy algebra. again, we could get a freshman at this point, second semester algebra student, we could say, what are the zeros of this function? They would say, well, there's a 0 at 0, there's a 0 here at 5, and there's another 0 at 8, and then we could take a pre-calculus student and we could, well, before I get to that point, let's go ahead and FOIL this thing out. I get Vx, I'm not taking derivatives yet, equals, I'm going to say x times, if I FOIL this, I get 160, I get minus 20x, I get minus 32x, and I get plus 4x squared. So I end up with, let's see, I get an 8x cubed. I get minus 52x's, so minus 52x squared when I distribute, and plus 160x. And here's what we would know from sprinters, intermediate runners, distance runners. This graph wants to go through 0. It wants to be going up really steep. Then it wants to be coming down in both directions, and ultimately it wants to go up to the right, down to the left. So everything about this wants it to go down this way. Going through here steep. I'm not trying to draw this scale where this is 1, 2, 3, 4. But eventually it's going to come down. But eventually it's got to go back up. This thing looks like this. We got our 3 zeros already. So we do not have an absolute maximum. We do not have an absolute minimum, but we do have a relative max and a relative min. But really, we're only allowed to be in here, so really what I have is just a maximum. Now, we could make an argument that, okay, maybe I want to conclude where the volume's 0 and these are less than or equal to. So we could maybe say that we have relative minimums here and here. But since they said 0 is less than x is less than 5, we're treating these like circles, and therefore there is no minimum within here. We never get down to 0. We get really, really close. But we do have an absolute maximum between 0 and 5. And that the only place that occurs is where the slope is 0, so of course we're going to find v prime of x. That is 24x cubed, 24x squared, excuse me, minus 104x plus 160. I want where the slope is 0, so I want to set, therefore I'm interested in this thing equal to 0. I'm going to divide everything by 3. Actually, I'm going to just write it down the way it is. So I want 24x squared minus 104x plus 160 equals 0, because I need a new space up here anyway. Now, slope is 0, so now it's an equation I can divide by 3, and I get 8x squared minus 26x plus, if I divide by, did I say by 3? I'm dividing by 4. So this is 6x squared, divide by 4, minus 26, divide by 4, plus 40 equals 0. All right, see if I can make it through here without another little error like that. And then I'm hoping this thing can factor. If I went quadratic formula, it would reveal my solutions for x as well, but I'm going to hope it factors. I need factors of 240. Nope. 6 times, yep, 240. That add up to be negative 26. Divided everything by 4. Everything looks like it's in good order here. I think we're in pretty good shape. Was this right here? Oh, wait a minute, back up. I knew something didn't quite feel right. This is 4x squared. How many of you are screaming at your computer? So this is 4x cubes. I get 12x squareds here, and this is 12x squared, and when I divide this by 4 I get 3. Let me rewrite that and start over at that point. 3x squared minus 26x plus 40 equals 0. Whew. I did not want to redo this video because of a mistake like that. Okay, so now I need factors of positive 120 that add up to be negative 26. Therefore, they must both be negative numbers. And again, you could quadratic formula this, but I'm going to do it this way. If they're both negatives, they get along to be 26. Well, how did I get there? I got there with 3 and 40. Those get along to be 43. That's no good. So I could steal a 4 from here, multiply a 3 times there, and I get 3 times 10, 30, that would get me to 120, and those add up to be 34, and I'm closer. I could steal a 5 from here, and that would leave me with 6 times 4, 24, and those add up to be 29, I'm closer. I could steal a 6 from here. If I steal a 6 from here, I get 6, I'm left with 5. I'm left with 4 times 5, 20, and those get along to be 26. So 6 and 20, this thing is factorable. Now, you may not factor this way. I'm going to say I need an outside product to be positive 6. This is really a cool way to factor as well as what you've learned at Hanamiga. To get a 6, I need a factor of 3 times a factor of 40. Well, that's 3x, and that is 2. And I want it to be negative, so that's minus. Now, first times first equals first. This is an x squared. Last times last equals last. Minus 2 times minus 20 equals plus 40. So either, don't know why that's x squared, that's just x. So either x is 20 thirds or x is 2. Well, 20 thirds is beyond my domain, so x equals 2 is right here. And you might have thought, hey, shouldn't it happen halfway between? Well, don't forget what's happening. It's trying to get steep here. Everywhere it goes, it's trying to get steep down to the left. So I believe it's steeper here than it is over here as it's flattening out. So at 2, the slope is 0 at 2. Therefore, f of 2. Do we want to go through this guy? F of 2 could be put 2 here, put 2 here, put 2 there. I'm going to do it that way. So I get 2 times, if I put 2 here, I get 10 minus 4, 6. If I put 2 here, I get 16 minus 4, 12. I get 12 times 12, 144, and that is a volume, so that would be like units cubed. Okay, let's test this. I'm nervous because I was making some mistakes there. Let's go y equals, let's clear this out. I'm going to enter it just how they did at the beginning here. I'm going to go x parentheses 10 minus 2x. And I'm going to go parentheses. Don't let me make a mistake here. Yell loud if you see one. Minus 2x. Parentheses. I know my domain is really 0 to 5, so I'm going to go to window 0 to 5. And if I set my domain, I like zoom fit, zoom 0. I bet you yelled at me somewhere. Y equals 16 minus 2x. Did I go 0 to 5? One more time, window 0 to 5. Up there it is. I know you were yelling at me. I knew that graph didn't look right. Zoom fit. That was another scary moment. I'm feeling good. Feeling good about my results here. Let's go second calc max. Second calc maximum. Let's get to the left. Come on, you can do it. Let's get to the right. Enter, enter. And give me a 144 there. Yay. 144. And it happens at 1.9999998. And that's us having to be smarter than our calculator. So we have a maximum at 2 of 144 confirmed. Interpret any value found in part A. Well, the maximum value of the box is 144 units cubed. Again, we could come back and argue about those at the minimum value is 0, but they really didn't let us go to. They stipulated in the problem. If we were coming up with this, doing this problem on our own, we might have said, well, it could be 0. Then we'd say that the minimum volume is 0. Support your answer to part A graphically, which we have already done. And therefore, we are through with this assignment. I've got an assignment list for you. Let me pull that up here real quickly. The remainder of this assignment is, rats, I wish I would have done this before. I'm going to read it to you and then I'm going to show it to you out here. Is page 198, 36, 38, 40, 42, 44, 45 through 50. This is interesting, all, and then 51. So why they said that, I'm not so sure. But anyway, there we have it. I believe that's all. You got to see it as I was writing it. And good luck to you. Lots of chances to make little mistakes, even though you do everything right. So be certain to be checking progress along the way, particularly on these ABC part problems. Great problems to be working with classmates. You can check, hey, did we get to there? Let's find our critical points. Did we get the same critical points? Let's find F of our critical points. Did we get the same F of values at those critical points? Make some determinations. Whole lot of easy. Enjoy.